Hello, welcome back. In this video, we'll discuss the materials and electrolytes for supercapacitors. Before understanding about the materials and the electrolytes for supercapacitors, we'll try to understand what a supercapacitor is. The supercapacitors are also called as ultracapacitors or electrochemical double layer capacitors. The supercapacitors are energy storage devices with very high capacity and low internal resistance. The supercapacitors are energy storage devices with very high capacity and a low internal resistance. The supercapacitors are able to store and deliver energy at relatively higher rates as compared to batteries due to the mechanism of energy storage. The working principle of supercapacitors is different from that of the batteries. Supercapacitors can store and deliver energy at relatively higher rates as compared to the batteries. Store energy and deliver at relatively higher rates as compared to the batteries, because the energy storage mechanism is different from that of the batteries. In the case of batteries, the chemical potential energy is released in the form of electrical energy, whereas here energy is stored in the form of static electricity, and that energy is released again in the form of electric energy. So they can store a very large energy. At the same time, they can also deliver energy relatively better than the batteries. Hereafter, we'll represent supercapacitors with SCs. Supercapacitors consist of two electrodes, an electrolyte or electrolytic solution. Thirdly, they will also have a separator. What this separator does is it isolates the two electrodes electrically. Of these three components, the electrode materials are very important in supercapacitors. Why they are important? Because the energy storage capacity and the energy density that can be stored in a supercapacitor very much depends upon the electrode materials. Hence, the electrode materials, they become very important in the supercapacitors fabrication. This is the structure of a supercapacitor. You have an electrode here, another electrode here. So there are two electrodes, and between the electrodes you have the electrolytic solution. This is the electrolytic solution. You have a separator that divides the electrolyte into two equal parts, and the purpose of the separator is to establish electrical isolation between these two electrodes. If this terminal is connected to positive of the battery, then you have the anions deposited on the surface, and similarly, if this terminal is connected to negative of the battery, we have the cations deposited on this surface. As a result, you'll have a capacitance here. The capacitance is represented with CdL1. The capacitance that is established at the electrode 2 is CdL2. So the entire structure acts as two capacitors in series. And in the circuit, we also have a resistor. The resistor is due to the electrolyte. Electrolyte is a liquid material, and the resistance offered by the electrolyte is represented with R electrolyte. This is the structure of a supercapacitor. We'll discuss some of the benefits of supercapacitors briefly. They have long life, high power, they can store high powers, they can also deliver high powers, flexible packaging. They can be operated over a wide thermal range, that is minus 40 degrees Celsius to 70 degrees Celsius. And they have low maintenance and low weight. They can be charged and discharged over 1,000,000 times. Energy storage mechanism. Basing on this energy storage mechanism, the supercapacitors can be broadly classified into three. The first type of supercapacitors are electrochemical double layer capacitors. The second one is pseudocapacitors. The third one is hybrid capacitors, or systems. In these three different classes of capacitors, the energy storage mechanism essentially changes. Now we shall look into the electrode materials. The electrode material is very important component in a supercapacitor because it is this element that determines the capacitance and the charge storage of the supercapacitor. We have three different classes of materials, namely the carbon materials, metal oxides, and thirdly conducting polymers. We shall discuss the carbon materials. The carbon materials in their various forms are the most used electrode materials in the fabrication of supercapacitors. Reason being, the carbon materials have high surface area, low cost, availability, and lastly, established electrode production technologies. These are the four reasons why the carbon-based electrode materials are widely used. Firstly, they have high surface area, they are low cost, they are available abundantly in nature, electrode production techniques are well established. When you use a carbon material, the energy storage mechanism is EDLC, that is electrochemical double layer capacitance. Of the carbon materials, the first type of carbon material that we discuss is activated carbon, for short called as AC. The reason why activated carbons are widely used is due to their large surface area, good electrical properties. The cost is moderate. Activated carbon is produced using two different mechanisms. The first mechanism is physical activation and the second one is chemical activation. Instead of having large surface area and the specific surface area of about 3000 meter square per gram, one find relatively small capacitance when the activated carbons are used as electrode in supercapacitors. The supercapacitor performance depends not only on the specific surface area but also on the pore size and distribution. In the case of activated carbons, the specific surface area is about 3000 meter square per gram. However, the capacitance noticed when activated carbons are used in supercapacitors is low. The reason is pore size and the distribution of pores is not in favor of increasing the capacitance. Now we will discuss the carbon nanotubes. A carbon nanotube is a nanostructure whose diameter is about nanometers and length is over a micron. The carbon nanostructures can be seen here. You have a conductive support over which the carbon nanostructures are grown. Each nanostructure has its own surface area and pore structure. The factor that determines the power density in a supercapacitor is the overall resistance of the components. A great deal of attention is given to CNTs, the carbon nanotubes, as supercapacitor electrode materials due to its unique pore structure, good mechanical and thermal stability, and superior electrical properties. The carbon nanotubes have unique pore structure, good mechanical stability, good thermal stability, and superior electrical properties. And these carbon nanotubes can easily be produced as well. There are two different types of carbon nanotubes, namely single-walled carbon nanotubes and multi-walled carbon nanotubes. These two different structures can also be used as electrode materials. Now we shall discuss graphene. Graphene is a one atom thick layer 2D structure of carbon. Graphene is a one atom thick layer 2-dimensional structure of carbon. So you have one atom thick structure, that is the graphene will be in the form of a sheet. Thickness of the sheet is about 1 atom. The structure will be spread in two-dimensional plane. So such a thing we call as graphene. The graphene has superb characteristics of high electrical conductivity, chemical stability, and large surface area. But the production cost of graphene is slightly higher. Among all the carbon materials that are used as electrode materials in electrochemical double layer capacitors, graphene is the best candidate with its specific surface area of 2630 meter square per gram. There's a huge surface area per unit mass of the graphene. So this large surface area increases the capacitance of a supercapacitor up to 550 farads per gram. Another important benefit we get when we use graphene as an electrode material in a supercapacitor is both the surfaces of the graphene can interact with the electrolyte because it's a very thin one atom layer structure. Next we shall discuss the metal oxides. The metal oxides, they present another alternative for materials used in electrode fabrication in supercapacitors because they exhibit high specific capacitance, low resistance. The commonly used metal oxides are nickel oxide, ruthenium dioxide, manganese oxide, and indium oxide. The lower cost of production and use of a milder electrolyte make them a feasible alternative to carbon materials. Next we will discuss the conducting polymers. Different conducting polymers have been widely researched as supercapacitor electrode materials due to their ease of production and low cost. Conducting polymers have a relatively high conductivity, they have high conductivity and capacitance and equivalent series resistance when compared with carbon-based electrode materials. There are different electrode configurations that can be used for conducting polymers. However, NP-type configuration is widely used. The NP-type configuration will have one negatively charged or N-doped and one positively charged or P-doped electrodes. The conducting polymers, when used, they offer high energy densities. The energy storage mechanism that is supported by the conducting polymers is the pseudocapacitors. One example for the conducting polymers is polyaniline, for short called as PANI. In this video, we have started our discussion by understanding what is a supercapacitor. We have seen the components of the supercapacitor. We have said a supercapacitor will have two electrodes, an electrolyte or an electrolytic solution, and a separator. We have seen the structure of a supercapacitor. We have seen the advantages of supercapacitors briefly, and we have seen the different energy storage mechanisms in supercapacitors. After that, we have started our discussion in electrode materials. We have said there are three different classes of materials: carbon materials, metal oxides, conducting polymers. The carbon materials are used because of the fact that they have high surface area, low cost of production, abundantly available in nature, and the established electrode production techniques. After that, we have discussed the activated carbon and the carbon nanotubes tubes. We have seen the structure of a carbon nanotube tube. We have seen the unique features of carbon nanotubes tubes. We have discussed the graphene and its uses as electrode material in supercapacitors. After that, we have seen the metal oxide electrode materials. Then we have seen lastly the conducting polymers, and one such example we have seen for conducting polymers is polyaniline. Thank you.